Well, here's another law, another relationship. This has to do with volume and temperature. How does volume change when temperature changes? There are conditions just like there were for Boyle's law, and here again it's a fixed amount of gas. You can't have the thing leak, and the pressure this time has to remain constant in order for this to work. Well, here's how you could write this relationship as a proportionality. You could say that volume is equal to some constant number times the temperature. And if you were to graph that out, here's what you'd find out. As temperature goes up, volume goes up, and it does so in a straight line relationship. So the equation for this line is actually going to be V equals K times T plus B. So there's going to be some y-intercept here, and that's because temperatures can actually go below zero if you're using degrees Celsius. And that creates a slightly problematic computational situation for physicists. And so they prefer to use the lowest possible temperature that can possibly exist. And you can find that by just extending this line experimentally and going back and finding out where does the volume actually become zero. Where would the particles not be moving at all and therefore not take up any space? And that turns out to be minus 273.15 degrees Celsius. That's the coldest temperature there can possibly be. So what scientists will typically do is they'll slide the scale back, and instead of working with temperatures in degrees Celsius, they'll start their scale right there. And if you do that, you get a different graph. The temperature in Kelvin against the volume starts right there, and it's a straight line relationship. Since it goes through 0, 0, then the relationship V equals KT plus B changes. There's a 0 y-intercept, and so volume is just equal to K times T. And you can make a two-point form of this. If you think about a relationship there, a point there and there, point number 1, point number 2, and I've got a temperature here, T1, and a temperature here, T2, and here I've got a volume, V1, and I've got a volume, V2. Both of these are on the same line, and the slope of this line is the K that we've got here. And so if I solve this relationship for K, I find that K is equal to V divided by T. So that means V1 over T1 is K, but V2 over T2 is also K. And so now we have a two-point form of that relationship. And remember, this only works if you use Kelvin temperature. Very important. This relationship is not valid unless you're using Kelvin temperatures. Here's an example problem. We have a volume of a balloon given to us in the freezer when it's 34 below Celsius. That's a temperature. Is 0.250 liters. The pressure inside the freezer is the same as the outside pressure outside the freezer, so that means constant pressure. We can use Charles' law. The question here is, what would be the balloon's volume? That's what we're trying to find outside the freezer, and the temperature outside is 25 degrees C. Well, let's set this problem up in this way. Volume freezer over temperature in the freezer is volume outside over temperature outside. Now remember, we have to use Kelvin temperatures here. So our temperature in the freezer is going to be the given temperature of negative 34 degrees C plus 273 to convert it into kelvins. And that's going to be 239 kelvins. So that's what gets inserted in there. So rewriting this, we can say volume in the freezer, that was 0.250 liters, over temperature in the freezer, 239 kelvins, is equal to volume outside, that's what we're trying to find, divided by the temperature outside. Well, the temperature outside was 25 degrees C. If you add 273 to that, you come up with 298 kelvins. So that's what goes down here, 298 kelvins. Kelvins are going to drop out. You do the cross multiply and divide thing, 298 times 0.250 divided by 239, and that gives you the volume outside, which is 0.312 liters, and that's an increase in volume when it gets warmer. That's what you'd expect to see according to Boyle's or Charles' law. Well, here's another relationship. This one applies constant volume as a stipulation, and it's for a fixed amount of gas, and we're looking at the relationship between pressure and temperature. the relationship turns out to be direct proportionality. Pressure goes up when temperature goes up. Or if we turn this into an equation instead of a proportionality, P is equal to K times T. And if you plot that out using Kelvin temperatures for the same reason that we use them for Charles' law, you find that you have this relationship, straight line relationship. And just like before, if you pick 2 points that are on the same line, which means same volume for a fixed number of gas, P2 corresponding to T2 and P1 corresponding to T1 are related in this 2-point form. P1 over T1 is P2 over T2. So there's a 2-point form for Amonton's law as well. And it's a very powerful problem-solving tool. So looking at this problem, we can solve it using Amonton's law. The pressure in a bike tire is given, 115 psi. It's in a heated garage. The temperature is 25 degrees C. The volume doesn't change, so that's valid to use Amonton's law. Question is, what's the pressure outside? That's what we're trying to find, P. And the temperature outside is 18 below Celsius. Well, we can set it up this way. Pressure in the garage over temperature in the garage is pressure outside over temperature outside. Well, we're going to have to change our temperatures again. So temperature in the garage, it said, was 25 degrees C. If you add 273 to that, you're going to get 298 kelvins for your temperature. And the temperature outside was minus 18 degrees C. Again, you add 273, and you're going to get a Kelvin temperature, and that's 255 kelvins. So plugging that information in up here, pressure in the garage, well, that was 115 psi. Temperature in the garage, 298 kelvins. Pressure outside, well, that's what we're trying to find. Temperature outside is 255 kelvins. Kelvins drop out. The units of pressure are going to be psi's. And if you do your cross multiply and divide thing, you find that the pressure outside is 98 pounds per square inch. It's a drop in pressure. You'd expect to see a drop in pressure when the temperature goes down. It would be nice to have a law that doesn't have the restrictions of Boyle's, Charles, and Amonton's law. They all had 2 restrictions. They all had one restriction in common, and that is that they always had to have a fixed quantity of gas. You couldn't change the amount of gas. And then the other one was dependent on the law. In Boyle's law, you had to have a constant temperature. In Charles' law, you had to have a constant pressure. In Amonton's law, you had to have a constant volume. But the combined gas law smushes all of these together and eliminates those restrictions and gives you a very powerful law. I'll give it to you in its 2-point form. P1 times V1 over T1 is P2 times V2 over T2. This very powerful law can solve any problem you could solve with Boyle's law, Charles' law, or Amonton's law. In fact, if any of those constants, if any of those quantities are held constant, you just revert to one of the other laws. Like, for example, if volume is constant, just take it out of here, cancels out, and now you've got Amonton's law, and so forth. Now, in using the combined gas law, it's very important, again, to remember Kelvin temperatures. Doesn't work unless your temperatures are in Kelvin. Here's an example problem. It's a plastic bottle. There's a volume of a liter on the beach. Pressure is given, 760 torr. The temperature is 30 degrees Celsius. The bottle is taken to the top of a mountain. The pressure drops. The volume changes. And the question is, what's the temperature? That's what we're trying to find. Well, let's set this problem up this way. The pressure on the beach times the volume on the beach divided by the temperature on the beach is pressure on the mountain times volume on the mountain divided by temperature on the mountain. We know our temperatures are going to have to be in kelvins, so let's do a little conversion there. The temperature on the beach was 30 degrees C. We'll add 273 to that, and we'll come up with 303 kelvins. So that's what's going to have to go in for TB. So pressure on the beach, we'll plug that information on there. Pressure on the beach was 760 millimeters of mercury, it said. The volume on the beach was 1 liter. Temperature on the beach, we just calculated that, was 303 kelvins. Pressure on the mountain was 400 millimeters of mercury. The volume on top of the mountain was 1.6 liters. And the temperature on the mountain is unknown. That's what we're trying to find. We find this by cross-multiplying. So I'll set the two diagonals equal to each other. First of all, let's cancel some units out. Millimeters of mercury are going to disappear, and liters are as well. So we have 760 times 1.0 times the temperature on the mountain equal to 400 times 1.6 times 303 kelvins. So the temperature on top of the mountain is going to be 400 times 1.6 times 303 kelvins divided by 760 times 1, or just 760. Kelvins are going to be the unit of temperature, and it comes out to 255 kelvins. Or if you wanted this back in Celsius, you could just subtract 273 from the 255 kelvins, and that would give you a temperature in degrees C, and that's minus 18.